Hello, Chem 1B. This is Chapter 20, Lecture Video 7, and we're going to be talking about fission, which, if you grew up in like the 1940s and 50s, you would have seen like propaganda posters that would be saying like, the power of the future. This is basically what nuclear power is currently based on. It's the power of the nuclear bomb and the nuclear power plant. Nuclear bomb being probably one of the most atrocious uses of science ever. A horrible thing. And the nuclear power plant, I would argue, is probably one of the only ways we're going to be able to supply enough energy if we try to get away from fossil fuels as due to their, climate change issues. Nuclear power is greenhouse gas neutral, so it does not affect climate change, which is very useful. However, it does have its pros and cons. Fission is where we bust up a part of an atom. So you can undergo fission with a bunch of different elements. Basically what we're doing is we're like hitting an atom with something and blowing its nucleus apart into smaller pieces. Now, the nuclear bomb and the nuclear power plant are typically based on the neutron bombardment of uranium-235 or an isotope of plutonium, depending on which one we're talking about. So what occurs here is when we hit a uranium-235 atom with a neutron, the nuclei gets blown apart into a bunch of small pieces, right? So here's our uranium-235 nuclei. We hit it with a single neutron, and it breaks apart into barium-140, krypton-93, and 3 more neutrons. This 3 more neutrons is very important, and we'll get to it in a second, but this is a heavily exothermic reaction. The amount of energy we can get from just blowing apart or the fission of uranium-235 is significant. So if we look at this equation, one of the things that is really important here is we used 1 neutron, we got 3. This can cause what we call a chain reaction. Because we're forming 3 more neutrons, and the fact that we usually don't have a single atom of uranium-235 in our sample, those other 3 neutrons that we just formed can run off and hit 3 more nuclei of uranium-235, which will then blow apart and form 3 more nuclei or neutrons each, which then, this ramps up pretty quick, right? For instance, if I have a sample of uranium-235 at what we call a critical mass, meaning you have enough uranium atoms there to start a chain reaction, you have a single nuclei hit, you form a lot of energy, and then each one of those neutrons that you made goes away, hits another nucleus. Now you form 3 more. So you just broke with 1, you broke apart so far 4, and then those 3 that we just broke apart are now going to form 3 more each. So now we're at 9 nuclei getting hit, and after 9 you have, I think, 27, and so on. So it explosively gets more and more collisions with our neutrons and the uranium nucleus, each time forming or releasing quite a large amount of energy. Now in a nuclear bomb, that reaction is just let go. They just start it, and if you don't do anything to slow the reaction down, the result is a nuclear explosion, which, not great in my opinion, and most people probably. The other way to go about this is to control the reaction, slow it down. What you can do is you can put the uranium in a neutron absorbing material so that not all 3 of the neutrons are going away and hitting more nuclei. They're hitting other things that don't have this type of reaction. And that's really what's going on in a nuclear power plant. They put the fuel rods or the uranium rods in a neutron absorbing liquid so that we can kind of control how quickly this reaction goes so that we don't get, this thing. All right, so let's look at a calculation of how much energy is actually being released in this type of scenario so that fission of uranium-235, there's some masses, and we can actually use the same equation that we did for nuclear binding energy, E is equal to delta M times C squared, to calculate how much energy is actually being released in kilojoules per mole from a fission reaction. And this will give you an idea of how much energy we can actually get out of this and why it's so appealing for our day and age when technology keeps requiring more and more electricity to power. More and more people have access to this technology and need that higher. There's always an increasing demand for electricity in the United States and in the world. So, okay, so the difference here is in the delta M, because we're not dealing with a single nuclei. Now we're dealing with a reaction. So instead of delta M being particles minus nucleus mass, it's, in this case, mass of the products minus mass of the reactants. So we need to sum up all the product masses and all the reactant masses. And once we have those, we can plug into our delta M, solve, use our E is equal to M delta M C squared, and solve for E. All right, so I'll leave that there. Now let's look at the products. So mass of the products first. Well, what do we got? We got some numbers here in our problem. We know the mass of barium-140 is 139.87988. And again, atomic mass units, same thing as grams per mole, so I'm just going to convert that so it's slightly easier to work with. I know that I have krypton here too, and we're given that mass here. So I know that that's 92.93127 grams per mole. And lastly, I need to add in my 3 neutrons that I made, right? So we know that a neutron is equal to, right here, 3 times 1.00866 grams per mole. Now I multiplied by 3 because we have 3 of them. So if I add all this up, that gets me the mass of my product. So let's calculate that. What we get is 235.837 grams per mole. So I got my product number. Let's look at my reactant number. So mass of my reactants. I have the mass of uranium-235. It was given here. So that's 234.99343 grams per mole, plus my 1 neutron, which we also have, 1.00866 grams per mole. And we can get that value. This is equal to 236.002 grams per mole. So now we can plug these in. Right, so my delta M here is going to be equal to 235.837 grams per mole minus 236.002 grams per mole. And this will give me negative 0.16496 grams per mole. Now this negative sign is important. It gives us the direction the energy is leaving. In this case, this is an exothermic reaction, so we should expect a negative energy, right? The other thing, just like before, we can't use grams in our E is equal to MC squared equation. We need to convert this to kilojoules. So I'm going to divide by 1,000 grams in 1 kilogram. So that will get me, negative 1.6496 times 10 to the negative 4 kilograms per mole. All right, so the last little bit here is just to take this number and plug it into our equation, at least close to the last little bit. E then is going to be equal to negative 1.6496 times 10 to the negative 5 kilograms per mole times 3.00 times 10 to the 8 meters per second squared. And I can calculate this value. What we get is negative 1.48. We'll just go to for sig figs. 5 times 10 to the positive 13 joules per mole of this reaction. Now, we were asked in kilojoules for an obviously good reason, so we're going to change from joules to kilojoules. So there are 1,000 joules in 1 kilojoule. This gives me negative 4.485 times 10 to the 10 kilojoules per mole. So hopefully you get the idea of why this is such a powerful use of our energy. It doesn't actually require that much fuel in order to get just significant amounts of energy, right? 1 times 10 to the 10 kilojoules of energy. We're basically doing 14 billion kilojoules per mole of fuel here, which is huge. So as always, if you have any questions about how I did this, you should be able to calculate the energy released in a nuclear equation. Now, for any reaction, just as long as you do products minus reactants for your delta M, you should be fine. So as always, please email me or come to a discussion session for any questions.